So, what we've done is developed a complete model that will represent a real transformer. We've got, in that model, we've got RM and XM together representing the core losses, the magnetizing current and the heating current in the core. Overall, it represents the exciting current that would flow regardless of load. And then in each side, we've got a reactance and a resistance. The reactance representing the leakage flux in that side, and the resistance representing the resistance of the windings. Sometimes they call them copper losses. You'll see them called copper losses in textbooks. Okay, so they're the effective resistance of the copper in that winding. So we've got this full equivalent circuit. Again, I want to emphasize that the terminals there on the secondary side and there on the primary side are the only ones in the real world that are electrically connectable to. They are your exit input and output terminals from your transformer. So this is like a theoretical model that will allow us to take account of the losses in the transformer. So what we're going to have to do for to finish off what we're covering today is have a look at doing this example. Okay, so I've given some values for the various components: 12 ohms for R1, 36 ohms for X1. Primary voltage is 11 kV. R2 0.008 ohms, 008 ohms, sorry. X2 0.03 ohms. Nominal secondary voltage is 400 volts, and a nominal rating of the transformer, the S for the transformer, is 100 kVA. Remember always that the S is associated with both sides. It's the same on both sides of the transformer. That can't alter. So if we put voltage up, current goes down, current up, voltage down. Alright? S should not be exceeded, otherwise we'll burn transformer out. Okay? So the first thing being asked to find in this problem is the transformer ratio I. How can we find that from the data we've been given? Yep. Remember, we can get that from either the voltage ratio or the current ratio or the turns ratio. So we haven't been given any turns, but we can get that from EP over ES, and you've not been given anything other than the nominal values, so you would use those. You know what the mean of the nominal is, the stated value, so what's on the nameplate of that transformer. So that's 11,000 over 400 comes out at 28, 27.5. Be careful about rounding that figure too much. Yeah, because remember, when you're transferring impedances, what do you do to that? You square it. So that's going to make any rounding bigger. Yeah, so be careful about. I'd always keep that to 3 significant figures personally, because you're going to square it when you do your transferring impedances method, and they're going to just you could introduce quite a big error. Okay, so I would recommend leaving that transformer ratio to 3 significant figures. Part B, full load current and the value of per resistance load that would draw this current. Okay, so this is full load secondary current. How are we going to find that? So that's asking for I2 at full load. From the information given, how are we going to do that? So what we can do is say here, S is I2 E secondary, yeah, which rearranges to I2 is S over E secondary. That's 100 times 10 to the 3 over 400 equals. As you rightly say, Luke, 250 amps. Yep. But the question didn't say that says find full load current and the value of per resistance load that would draw this current. Yep. So therefore, RL, how are we going to find that? We've got a current now, we've got the current going through it. We have, because we're assuming full load, we're assuming nominal here, so that'll be 400, won't it? Yeah, so that's ES over IL 400 over 250 equals 1.6 ohms. Yep. So we've now determined that if we're going to analyse this full load condition, we've got 1.6 ohms connected to there. Yeah. We'll use nominal values to get that far. What we need to do now is so that we can analyse the effect of these two components and these two components, we need to simplify this model. How did we do that last week? Shift the impedances across. Yeah? So what we got to do is shift all three, that one, and that one, across to that side, and then we've got a simplified model. We can then transfer back later to find the information that we want. So that's part C is the value of the three secondary impedances reflected to the primary side. So, change colours there. Part C, we've got to find RL dash. How do we, what do we do when we want to reflect it across an impedance? Multiply it by I squared, yeah. Which is 27.5 squared times 1.6 equals 1210 ohms. Yep. And we've got to do R2 dash, again that's A squared times R2, 27.5 squared times R2 was 0.03 ohms, .7 ohms, and x2 dash is A squared x2, that's 27.5 squared times 0.008 equals. I have that wrong. I got them the wrong way round. That is actually, please, because that's the value of x2, means my worked solution is now completely wrong, but never mind. The answer to that is, sorry, 6.05. The ohmic value of the inductance is in general much bigger. The leakage inductance is much bigger than that for the resistor. That's what flagged up to me, have I got this the right way round. I was looking at that result after rewrite those solutions. Okay, so my results are not good anymore. We're on our own now. So what we've effectively done, I'm going to go on to a new page here because we've now got a new model. There's our generator voltage. They're the two terminals EP, that's 11 kV. We've got an R1 and an X1 in series with R2 dash and X2 dash, RL dash, like that, and our transformer is now in there and redundant in terms of that. Let's put some values on there. R1. Just right, so that's our transferred impedances transferred to the primary model with either the given values or the calculated values added for the transferred and components in the primary. So what we've got now is a current flowing there, which is I1, and that's also equal to I2 dash. Yep. So, what's the next part of the problem? Next part of the problem is the primary current if the fully loaded transformer is supplied with its nominal primary voltage. So how are we going to go about finding I1? That's a fully loaded situation because we put 1.6 ohms on it and then transferred it across. So what is the first thing we need to do to find that current flowing? No. We know S, or we know the nominal S is 100,000 kVA. 100 kVA, sorry. Yep. That's not going to help us. Remember, in theory we could get it from that, but in loaded practice we got to take into account losses. So we're assuming now we're going to apply 11,000 volts to there. How can we calculate the current flowing through that, what is essentially, remember this bit ain't doing anything anymore, we can ignore that. So we've got a series circuit, we've got to find total impedance ZT. What's special about that total impedance? It's going to be a sort complex, yeah? You're saying the same thing, it's complex. So it's going to have a resistive component made up of these three resistors in series. So it's going to equal R1 plus R2 dash plus RL dash as its in-phase component, isn't it? And then these are reactances, so it's a plus X1 plus X2 dash J. So we can just add up all the series resistances to get an overall resistive part, and add up all the series reactances to get an overall reactance part. What we're effectively doing is turning that circuit into one resistor and one reactance in series. You all okay with that? So we put the numbers in. So that's the numbers in full. Put the extra step in if you like. You can actually put it in a calculator like that, but it might be as well to put the extra step in. Those three added together come out as 1,258.
Plus 58.7J.
Oh yeah, because 58.7.
J,
And what I tend to do these days is also, you might want it in that form, but you might also want it later in polar form, so probably write it down in both forms. So convert that to polar as well.
so when I'll just put
1229 ohms, angle 2.73 degrees. Yep. So we've got the total impedance, so we can say therefore I1, which is equal to I2 dash as well, probably worth saying that, and that's going to equal E primary over ZT. So it's 11,000 divided by this 1229 angle 2.73 equals. That is 0.8. 11,000 divided by 1,000.
It's 8.95. So
8.95. We'll keep to 3 sig fig. Yeah. Angle minus 2.73. Yeah. Right. So the next bit is saying find I2. That's the real current I2 in the secondary. We've found I2 dash. So we can also say about I2 dash is equal to, i.e. how do we transfer an I2 to a current in the primary? How do we reflect the current? Divided by A. So is equal to I2 over A. Therefore, I2 must be A times I2 dash. Agreed? So that is 27.5 times 8.95 angle minus 2.73. So that's your current flowing in the secondary. Remember what our nominal current was for maximum rating was 250 amps, wasn't it? So we lost, because of them other components, and we've ignored the core losses here, we haven't calculated them, but we lost 4 amps to what we should do. Yep. So the last bit says, find the apparent power delivered to this load. So how are we going to do that? We now know the secondary current, actual secondary current flowing through the original load, the 1.6 ohm resistor. How can we find the apparent power S? What else do we need to find the apparent power S? Yeah, or E2 times the current. We found the current, so what we need to do now is find E2, don't we? Yeah. So how to do that? If we can find E2 dash, yeah, which would be this voltage across here, across the load, we can transfer that back to the other side and then use that with the current we just calculated to calculate the actual apparent power delivered to this load. Agree or not?
yeah. So when we found ZT, you need to sort of do that again, but exclude RF.
And actually this is going to be, yeah, E secondary dash, that is. Because that's just the voltage across the load resistor. That's representing the load resistor, isn't it? But reflected to the primary. So if we use the current we just calculated, I2 dash, or I1, and that resistance, we'll find ES dash. We can then transfer that back to the other side and use that with the current we just calculated, 240 odd amps, to find S. Are you following that? We've got a primary current flowing through here, Luke. Yeah? Right? This resistor here is the reflected value of the load resistor, 1.6 ohm resistor, we connected in to the secondary in the original diagram. Yeah? It's the one that, in theory, would draw the maximum load current. Yeah? But we've reflected that into the secondary, so this is the value in the primary, that represents that 1.6 ohm resistor. Yeah? So if we calculate the voltage reflected into the primary across that resistor, we can then bung it back the other side and calculate its value when it's in the secondary, and then we can use that to find the S being delivered to the load, the apparent power being delivered to the load. Yeah? Because we're delivering a certain apparent power to these two terminals that will be the current times that voltage, but some of that apparent power has been lost in these four components at the top here, isn't it? So not everything being drawn from the generator is not being delivered to the load. There's losses. That's what all this is about. We've got a real transformer now with losses. Okay? So if we use Ohm's law, with that current, I1, and this resistor value, we'll get a value for that voltage that we can then transfer back the other side. Must be, E2 dash must be I1 times ZL dash. That's, sorry, yeah, that's ES dash. Well done, Tom. Got to be particular. So that must be 8.95 angle minus 2.73 times 1210 angle 0 degrees. To be complete. Right, isn't it? ZL dash is 1210, yeah. So one push the buttons. We only need to calculate the magnitude. The angle's not going to change. Just per resistor. Nearly 9 times 1,000. What did you say, Danny?
108.30.
Equals 10,830 volts at angle minus 2.73. So that 11,000 volts that we're applying has now dropped. We lost 200, nearly 200 of it across internal components. Yep. What we've now got to do is transfer that to the other side. How do we get a secondary voltage transferred to the primary using the ratio? The current is divided by A. It's A times ES. Therefore, the actual ES is ES dash over A. We're going back the other way now. We're going back from primary to secondary, aren't we? So we've got 108 2.30 angle minus 2.73 over 27.5 394 volts angle minus 2.73 degrees, and they're both at the same angle. We got a per resistance. We could just multiply the magnitudes together now to get S2 is equal to I2 E2. That's 200 and how many amps was it? 240 something. 246.1 times 394 equals 96,900. VA equals 969. No, 96.9 kVA. Yep. So nominally we connected a load that should have completely loaded up to 100 kVA. This transformer actually delivering to that load 96.9 kVA. Yep.